Yeah, welcome to this GATE crash course. Right. And today's topic is random process. I will be myself, Anup, will be handling this topic, random process, and I'll also be handling the first part of electromagnetics, that is Maxwell's equation and wave propagation part. So, this random process, right? So, it in itself is a vast topic, so we can't discuss everything. But if you see the gate questions, right, what we can see is there are certain areas which they concentrate, right? Someone is trying to join. Just right. So there are certain areas which they will concentrate. So what we'll do is we'll try to focus in that particular area, right? Before we start with, right, so we should have some clarity. What actually is this random process? You should at least be able to differentiate between a random process. Whenever I write random RP, it means actually what random process and random variable, right? So you should be able to differentiate between this, and there is something called sample function, right? Sample function and sample value. So I'll be using these terms, right, throughout the discussion, right? So initially you should be able to differentiate instead of going by actually definition. What we'll do is we'll take a typical example, and with that example I'll try to explain what is a random process, what do you mean by random variable, right? What is sample function, sample value, also what is meant by ensemble average, what is meant by time average, right? All those aspects initially. So we'll take an example. So you take an example of suppose we have a resistor, right, whose values are, and you have studied about thermal noise, right? So because of this thermally activated electrons, and they will be in Brownian motion, so it will constitute some uh, current, or right, so that motion will constitute some net current at any given instance, right? So that actually is it's a typical example of what a random signal, right? So if what we are doing is, if we are creating infinite number of such resistance, all are similar type of resistance, and we are trying to uh, record what is the output current produced by this thermally activated electrons, right? So for each, so we are creating almost infinite number of such resistance. So if you note down these outputs, right, so it will be something like this. So for first resistor, if you measure, it will be like this. Second resistor, third resistor, right? So these are completely random, right? And you can see at any given time, right, it will have some finite value, right? So if you, so this is a random process is actually what it will be a random variable as a function of time, right? As a function of time, if you plot, right, so it can be anything. If you consider a discrete random process, can be actually what rolling a die, right, or tossing a coin. So in those cases, the outcomes are actually what maybe a discrete, right? It can take only discrete from a discrete number of values, but in this case, it can take values. It can have continuous values, right? So a random process is actually what, if you are a random experiment's outcome, if you are associating with some real value and plotting it as a function of time. So for instance, x of t. So this is a random process. A typical example would be a thermal noise, right? Thermal noise which is plotted as a function of time, right? So these are different actually what sample functions, right? So this is for one resistor, this is for other resistor, right? So all these are actually what different sample values, or you can tell, if you are if you are observing the output of or thermal noise output, it can be any one of these. So in this case there can be almost infinite number of possibilities, and it can be any one of these. And if you consider any given time, say time t1, you consider, right, at that point each sample function will take some value, right? Each sample function will take some value. So that is actually what I'll be, whenever I say random variable, right? So it can be what the a value taken by this random process at any given time instance. So that will be actually what random variable. So random process is a function of time. Random variable, it can be considered as the uh, sample value taken by a random variable at any given time. So this is random process, random variable, and sample function. Each of this are actually what sample functions. So in this case, we can have infinite number of say sample uh, functions, right? But if it is actually what rolling a die, right? So the sample functions will be actually what 1 to say 6. There will be finite number of sample functions, but in this case there will be infinite number of sample functions. So what happens is normally, right, when you say ensemble average, so these set of sample functions, exhaustive set of sample functions, right, all possible sample functions are called actually what set of all possible sample functions we'll call ensemble. And if you take average, for instance, expectation of x of t1, right? So if this is an ensemble average, it is nothing but what average of all these points at a given time instance for all different sample functions. That is ensemble average. And but in most of the time, in the case of for example, in the case of thermal noise, we cannot populate all possible outcomes, right? So it's not possible. So instead of that, instead of finding out average over different uh, samples or different sample functions, what we can do is we can take time of, we can consider a single sample function and take average over a time. So that is actually called that is called time average. The time average is, if you can, it is say 1 by 2t, right, over a period of 1 by 2t minus t to t, right, this x of t dt, right? So this will be time average. But whereas ensemble average will be average taken at a given time instance across different samples, right? So normally we don't have to bother about this. Mostly in gate we'll get questions from ergodic process or wide sense stationary process. So in a wide sense stationary process, this ensemble average and time average both will be same, right? So we'll be in further discussions, we'll be assuming actually what a wide sense stationary process wherein ensemble and time average both will be same. So with that small introduction, we'll start with our discussion. Initially, uh, what I'll do is we need to have some basics. Some basics we need. So we'll discuss those basics, and then we'll move on to our autocorrelation function and PhD and their properties. So mainly questions are asked from properties of autocorrelation function and power spectral density. Right. So before that, right. So any random process or random variable you consider. So if x of t is a random process and x, right, is a random variable, right, and small x, right, so this is a random process, x of t is a random process, right, this is a x can be a random variable, which means it is the sample value which can be taken by this x of t at any given time instance. And the small x, right, if it is a sample value, right, if it is a sample value, right? So now in this case, right, we can first, you should know what is a probability distribution function, probability distribution function, or cumulative distribution function. That probability distribution function, it is also called actually what cumulative distribution function. Anyone know what actually is that? Okay, normally we represent it as capital X. So capital F of X, right? This is the probability that a random variable x takes a value less than or equal to x, right? So this is called actually what probability distribution function or cumulative distribution function. This is a probability that a random variable x takes a value less than or equal to small x, right? So and it will range from actually what this minus infinity less than or equal to x less than or equal to plus infinity. This x can take values from minus infinity to plus infinity, right? So this is a probability distribution function. So some of the properties of probability distribution function I list down, right? So that will be, what will be f of say infinity, right? What will be probability f of infinity, which means probability that x takes a value less than or equal to plus infinity. This will for sure be equal to 1. Why? Because the range of values that can be taken by x is from minus infinity to plus infinity. So this probability distribution function, it says what is the probability that x takes a value less than x. So the probability for x taking a value less than plus infinity, no, anyhow the value of x will be less than or equal to infinity. So that is equal to 1, right? And probability of minus infinity, right? What will be, can anyone tell me what is probability of a cumulative density function of minus infinity? That is probability that x less than or equal to minus infinity. Can anyone tell me what is that? You can unmute and tell. Right. So this will be equal to, see, 0. Right. And further, right, we can say, right, f of x2 will be greater than f of x1 if x2 is greater than x1. Of course, right, if you're considering two sample values, x1 and x2, if x2 is greater than x1, f of x2 will be greater than f of x1. So this f of x1 will be, right, the probability that this random variable takes a value from minus infinity to x1, and similarly f of x2 will be probability that the random variable takes a value from minus infinity to x2, right? So of course the probability for a random variable being less than or equal to x2 will be greater than that of x1, right? So these are the properties. Maybe at times, right, may not be in gate, maybe in some other competitive exams you may get, right, straightforward questions like this from these properties, right? So please do note it down. And one more thing, the slope of this cumulative distribution function, that is d by dx of f of x, it will be always positive, it will be always greater than or equal to 0. So these are some of the properties of say probability distribution function, right? So what we have seen is probability distribution function is probability that a random variable takes a value less than or equal to x, right? So next aspect which we should discuss is uh, probability density function, right? Probability density function. So we'll represent it as small f of x, and in some cases, right, we'll write it as for f subscript x of x, and also we'll be using to further simplify this notation, we'll be using small f of x, right? So this is nothing but what, this is small f of x, right? Small f of x, it will be yeah, small f of x will be equal to d by dx of capital f of x, right? It will be d by dx of capital f of x, that is derivative of capital f of x, or in other words, capital f of x will be integral from minus infinity to say x f of x dx, right? So this right, it's the density function. It more or less gives what is the probability that right, so it gives probability that x equal to small x, that is what is the probability that x is equal x to take a value equal to some sample value, right? So this is a probability density function. So normally we'll represent it as pdf, right? So if it is mentioned as pdf, right, so maybe we'll get confused whether it is probability distribution function or probability density function. So normally if it is, unless otherwise mentioned, if in question it is mentioned as pdf, that can be probability density function. That is actually what derivative of probability uh, distribution function. So probability distribution function, it is also called called as actually what, cumulative distribution function. So I know you may be getting confused, but we'll solve a small problem now, so then your confusion will be solved, right? So now some of the properties of this probability density function, right? So we know this f of plus infinity, right? F of plus infinity, we know f of x, fx of x, f of x is equal to minus infinity to infinity fx of x dx. So f of plus infinity will be minus infinity to infinity f of x dx. So we have already seen in previous page, right? Probability that a random variable is less than or equal to infinity is always 1. So this is equal to 1, which means area, right? Area under probability density function graph is equal to 1. So that is one a very important result. You should keep that in mind, right? Area under probability density function, that will be equal to 1, right? Then one more important result which will be useful is probability that a random variable takes a value between x1 and x2, right? Probability that a random variable takes a value between x1 and x2 can be computed as integral from x1 to x2 f of x dx, right? So this is the probability a random variable takes a value between x1 and x2, right? So maybe the proof or how it came, all those aspects I'm not discussing, but these are actually what straightforward. These properties follows from the basic definition itself, right? So maybe now we'll see an example, right? We'll see an example, right? So this different probability density functions are, right? Different PDFs are, one is actually what you might have heard of uniform probability density function. So what is uniform probability density function, right? So right between, so the probability for, so this of, I'll write it as f of x. So x will take any value between a and b and with equal probability. So this, it will be equal to 1 by a minus b. So a uniform PDF, the PDF can be written as, you just note it down, f of x, this will be equal to, right, the probability is same, 1 by b by a, right? That is, the area under this has to be equal to 1. So if the range of x is from a to b, right, and the probability is same, for this area to be equal to actually what, a unity, right, this height should be equal to 1 by a minus b. So the length is b minus a, right? So the height should be equal to 1 by b minus a, right? Sorry, so this length is b minus a, this much is b minus a. So for this area under this graph to be equal to unity, this height should be equal to inverse of that, 1 by b minus a. So when you multiply b minus a and 1 by b minus a, you will get area of the rectangle to be equal to 1. So we can represent it as actually what, 1 by b minus a into u of x minus a minus u of x minus b, right? Where u of x is actually what, the step function. U of x is step function. This is u of x, right? So 0 and 1. So for positive values of x, it will be equal to 1, and for negative values, it will be 0. So u of x minus a will be u of x shifted, u of x minus a will be u of x shifted right by an amount a, and u of x minus b will be u of x shifted right by an amount b. So if you subtract these two, what you will get? You will get this shaded region. So that's actually what, probability density function. So what will be probability distribution function of this? Probability or cumulative distribution function of this? Cumulative distribution function, right? It is given by, it will be CDF, that is capital F of x, will be at any given x is given by integral minus infinity to x f of x ds, right? But if you see this, you can see from minus infinity to a, right, the probability of x being, x taking a value between minus infinity and a is 0, right? So if you plot this probability, so if you plot here, right, I'll plot here, the maybe intuitively we can just plot before we evaluate this, right? So for it to take values from minus infinity to a, right, the probability is 0. So if you integrate from minus infinity to a, the probability has to be equal to 0, right? But from a to b, you can see if you consider, if you right area, if you're considering maybe a to this a plus delta, this is the area, right? A to a plus 2 delta, this is the area. So area is actually what increasing linearly. So the probability density function will increase linearly, right? It will be, by the time it reaches B, what will be the area, right? This is actually what area of the strip, right? Area of the strip. If you consider the largest strip, area will increase. Further, largest strip area will increase, and this area will be a linear function of actually what, x, right? So, and the at B area will be equal to actually what, 1, and further, as the probability is 0, right, it will be 1. So this is the probability distribution function, right? Probability distribution function. So if you integrate this, if you perform this integration, I'm not doing this, right? So you will get this to be equal to what, x minus a divided by b minus a, right? So the slope of this will be actually what, b minus a, right? And right, so it's a straight line. It's not actually what passing through origin. If it was passing through origin, it would have been actually what, x by b minus a, right? Only so that y-intercept would have been 0. But now what happened is this is shifted right by an amount a. So instead of x, we have x minus a. So this integration part I'm not doing, right? So if you integrate it, for sure you will get a result like this. So maybe I can write it. So it will be equal to 0 for minus infinity less than or equal to x less than or equal to a, and it will be equal to x minus a by b minus a for a to b, and it will be equal to 1 greater than or equal to b. So this is the probability distribution function. So probability density function is the probability that a random variable takes any given value, right? And probability distribution is what is the probability that it is less than or equal to a given value, right? So in this example, so you can see that, and some more commonly asked questions. Some more commonly asked questions are, maybe one more possible distribution is Gaussian distribution, right? Gaussian distribution. Normally, normal Gaussian distribution. Normal distribution means mean will be equal to 0, variance will be equal to sigma square. So the plot will be a Gaussian bell. You all are familiar with this, right? So it will be centered at 0, right? And the probability density function in this case is f of x is equal to 1 by root 2 pi e power minus x square by 2 sigma square, right? E power minus x square by 2 sigma square. And if you find, so this right, what will be the value of this function when, okay, this is f of x, right? So this will be equal to 1 by root 2 pi when x is equal to what, 0. So the corresponding probability distribution function will be, you can see the this is actually what symmetric about x is equal to 0, right? So on the area on negative side and positive side, both are same, right? So if you find the probability distribution function, it will be something like this. It will be increasing, right? Increasing, and it will be becoming a constant. So this will be equal to 1, and this will be 0.5, and this is our f of x. Normally they used to ask, they may give a function, right, a Gaussian function, which is the probability cumulative density function, or probability or cumulative distribution function, or probability distribution function they used to ask. So in that case, this is the answer. And similarly, I request you to find for if it is a Rayleigh distribution, right? Rayleigh distribution, and if it is say exponential distribution or Laplace distribution, what will be the case? If you can just have a look. So because of this, as we have to finish entire thing in one session, I'm not discussing all these things, but you can just see if it is say a Rayleigh distribution, it will be something like this. The probability density function, and probability distribution function. You can see it again will start from 0, and it will be something like this. It will all the way go to 1, right? So this is for Rayleigh function. So I request you to just go through that. So the basic ideas, probability distribution function and probability uh, density function. Are you clear with this? Probability distribution and probability density function. Can anyone give me a feedback? At least some idea. Are you able to note it down, whatever points I'm telling? If you are not able to appreciate, as we have time constraint, I'll be listing down the results. Right? Are you able to follow this? Yeah. So please note it down. Right? Maybe at the end, if you have if you have any further problems, we'll discuss it in group. Right? Right. Not a problem. Right. So fine. So now what we'll do is we'll proceed further. Right. So now we'll proceed further, and now we have discussed about probability density and probability distribution function. So if it is joined, right, if it is joint probability density function or joint probability distribution function, so then if it is f of x comma y, it is nothing but what? Probability that x is less than or equal to x and y is less than or equal to y. So this is joint probability, like joint probability distribution function. So normally if it is probability distribution function, I'll write it as CDF, right? Joint CDF. So in this case, f of x comma y, you can just note it down. F of x comma y, normally in our one dimensional case or single variable case, it was actually what? Dou by d by dx. So in this case, it will be dou square by dou x dou y of, right, f of x comma y. And similarly, f of x comma y will be integral minus infinity to x, integral again minus infinity to y, right? F of x comma y dx dy, right? F of x comma y dx dy. So in a single variable case, right, if you integrate this probability density function, you are getting an area, right? In single variable case, it was something like this. If you integrate it, you will get some area. But in this case, this is a plane, right? This is a plane. So if you integrate, you will get a volume, right, in joint PDF, right? So I'm just mentioning this. Please keep this in mind. So in joint probability statistics, right, probability characteristics, right? So when you integrate, right, PDF, you will get a volume, and this volume under this, right, volume, it will be total volume should be equal to 1. Or if you integrate minus infinity to plus infinity, minus infinity to plus infinity, right, f of xy dx dy, that should be equal to 1. So please do keep that in mind, right? So those are some of the very basics which you should know, right? So now with that note, we'll move on to what next aspect, that is statistical averages. So from this point, you can expect actually what some problems in GATE. So statistical. So I know I'm going a bit fast and I'm like skipping some aspects, but right, these points, if you note down, right, maybe if you have some doubt, we can always discuss it later, right? So, and so first one is actually what? Expectation of a random variable, E of x, right? So this is actually what we'll also call it as mu x or mean of x. This is defined as minus infinity to infinity x into f of x dx, where this f of x is nothing but what? Probability density function. So normally, right, this is by definition, normally for GATE, right, we won't have to use this. Maybe we'll be given autocorrelation function or power spectral density. From that, we'll have to find mean, variance, all those things. We'll solve such problems, right? So maybe I'll take 5 more minutes to list down all the important results, then we'll start solving problems. Then I think it will be right, more interesting. Then if, right, so we can have function of, if x is a random variable, right, we can have function of random variable, right? That is also possible, g of x. So in that case, expectation of g of x, what will be expectation of g of x? It is nothing but what? Integral minus infinity to infinity g of x into f of x dx, right? So this is expectation of g of x. The next one is very important, I think, that is mean square value. When I write MSV, it is mean square value. Normally the questions which you used to get in gate is a random variable will be given and find the mean square value, find the mean value, right? All those things. So mean square value, when I write MSV, it is mean square value, right? It is nothing but what? Expectation of x square, right? Expectation of x square, right? So it is nothing but what? My integral minus infinity to infinity x square f of x dx. So mean square value is expectation of x square. This is x square f of x dx. And please keep in mind, this will be actually what? Average power, right? If you are asked to find average power of a random signal, right, it will be nothing but what? The mean square value, right? It will be mean square value. So I hope you are able to note it down, right? Please do note it down. We'll be what? Recollecting it while solving problems, right? So then another important result is variance, right? Variance of x, right? Variance of x is nothing but what? It is, maybe you might have studied it as actually what? Second central moment, right? So mean square value is second moment, right? E of x square, right? Variance is second central moment. Central moment is E of x minus mu x the whole square, right? So it is x minus mu x the whole square. So as we know, this expectation is a linear operator, right? We can write it as E of this x minus mu the whole square. We can expand it is x square minus 2x times mu x minus mu x, sorry, plus mu x square, right? So as this is a linear operator, we can actually what? Write it as it is equal to E of x square minus 2 times this mu x is mean, that is again is a constant. So 2 times mu x times E of x, right, plus E of mu x square. So this is again a constant. So expectation average of a constant will be constant itself. So we can that this is a very important result, right? This is a very important result which I'm going to discuss here. So this E of x square is nothing but what? This is our mean square, means MSV, mean square value. E of x square is mean square value. So this is, I'll write it again. So this is MSV minus 2 mu x into E of x again is actually what? Mu x. So it will be minus 2 mu x square plus E of mu x square will be mu x square itself. So this will be MSV minus mu x square, right? So variance of x, this is a very important result. Variance of a random variable, right? That is nothing but what? Mean square value minus mu x square, or else we can write MSV minus mean value square, right? MSV minus mean value square. This is variance of x. So this again, it's right. We used to get many questions from this particular aspect. And what if mu is equal to 0? For instance, in a normal Gaussian distribution, mu is 0. So then this mean square value or average power will be equal to variance. You might have used it in many places, right? Average power you might have computed as variance in many cases, especially in communication systems, right? So this is again a very important result. Then what we have is, right? So no, I have told we have, right, many sample functions in ensemble, right? So right, so we are interested in, right, how right, these random variables are correlated with each other, right? At time equal to t1 and time t equal to t2, right? How they are interrelated. For that we have actually what? Something called autocorrelation function. It will give you maybe what? Similarity, right, or periodicity, whatever, right? I'm not going into detailed theoretical aspects, but whatever is exactly required to what? Solve problems related to gate, that's what I'm discussing here. So normally we'll represent it as Rx of t1 comma t2, right? So Rx of t1 comma t2, that is nothing but what? Expectation of x of t1 into x of t2. You know what is expectation? That is an integral, right? So this is expectation of x of t1 into x of t2. So that is actually what random, autocorrelation function. So now, most of the questions in GATE, it comes from actually what wide sense stationary process. WSS is wide sense stationary process. Right. And now I would like to make a comment. So most of the the random functions which are coming in a communication system, right? Those can be modeled as something called ergodic process. I mentioned what is an ergodic process. If time average and ensemble average both are same, right? That is called actually what ergodic process, right? So this white and stationary process, it's actually what it's when I we can say a process is white and stationary if it actually what satisfies two conditions. So its mean is actually what if its mean is constant, right? If mean is constant, right? And autocorrelation function, I'll write ACF is a function of, please note it down, right? Time difference. Autocorrelation function is a function of time difference. I'll tell what is that actually. So for instance, if you are considering two samples, right, at t1 and t2, which is separated by time tau, right, and you are considering some other two sets, those are again separated by time tau. Say it is at t3 and between t3 and t4, right? So now what happens is autocorrelation function Rx of t1 comma t2, right? This will be equal to what? Rx of tau, right? Rx of tau, right? So and this can be written as actually what? This is equal to expectation of x of t into x of t plus tau, or you can even write it as expectation of x of t minus tau into x of t, right? Where tau is actually what? Time difference. So for a wide and stationary process, right, autocorrelation function, it depends only on time difference, right? If you take two samples which are actually what equally separated, which are separate, if you two sets of samples, right, which are equally separated, then the correlation functions, it will be same. So that is actually what. So if these two conditions are satisfied, that is actually called what wide sense stationary process. And one more thing, for a wide sense stationary process, this Rx of tau will be equal to what? Rx of minus tau. It will be an even function. So it will be autocorrelation function will be an even function. Autocorrelation will be an even function. So this is um, about wide sense stationary process, right? So then what we'll do is we'll just see some of the properties of autocorrelation, right? So this is going to be very, very important, right? Properties of autocorrelation. Right? I know I am going a bit fast. Right? Do you want me to reduce the pace? Right? I didn't intentionally ask because I'm given a time of 1 hour to finish the aspects, right? So maybe I think I should stop maybe at least for 30 seconds and would ask your opinion. Can I go in this pace? Initially, I list down all the important results, right? Then what I'll do is we'll right solve at least one problem. We'll try and solve today, right? Is it okay?
Yes, sir.
Yeah. Okay. Fine. Thank you. Right. So now properties of autocorrelation function. And now itself, if I may request, can I extend till 440, 455 or something? Would that be fine?
Yes, sir.
Yeah, okay, thank you. Right. So first one is it's an even function. Autocorrelation function is an even function, that is Rx of tau is equal to Rx of minus tau, right? And second one is right Rx of 0, right? Rx of 0 means time difference is zero. If you are trying to find the similarity of a random signal with itself without any time delay, right, that will always be greater than or equal to what? Rx of tau, right? So if you take any small time difference, right, the autocorrelation function will be what? Less than the autocorrelation function with no time difference. These are actually, this follows from the basic definitions, but these, from these properties you used to get, so they used to give some results, then write which are true, only one is true, one, two, three are true. So for such questions, these properties as such they may ask, right? So Rx of tau is greater than or equal to Rx of 0 is greater than or equal to Rx of tau, right? So then next one is, right, mean value square. So mean value is actually what? Or mu, right? Square of mean value, right? So one more thing which you have to keep in mind, if you consider any signal, right, average of that, average of that is actually what? It's DC value, right? Even if it is a sinusoid or any signal as such, right, mean of that signal, right, if you're asked to find the DC voltage, what you should do is you should find mean voltage, right? So DC value is actually what? Mean value. So square of that DC value will be, right, I'm writing it as mean value square. This will be nothing but what? DC power, right? Please note it down, right? This will be nothing but DC power, and in terms of autocorrelation function, this will be equal to, please, limit tau tends to infinity Rx of tau, right? So DC power will be limit tau tends to infinity Rx of tau. For instance, if autocorrelation function is something like this, right? So 0, say minus 10, 10, it spans till infinity, and this is 50, and this is 20, right? What will be limit tau tends to infinity Rx of tau in this case? So when this is tau actually, as tau tends to infinity, the autocorrelation function will be equal to what? 20, right? So that will be the DC value. What is the value of autocorrelation function at tau equal to infinity? That will be DC power, that is mean value square. So then what will be this mu or mean value? Mean value will be square root of limit tau tends to infinity Rx of tau, right? So this again is a very important result which will be helpful in solving problems, right? So please do keep this in mind. Then now we have mean, right? So then one more important aspect is mean square value, right? Mean square value, right? So mean square value will be equal to Rx of 0. So this mean square value is nothing but what? Average power in a signal, right? Average power. So maybe those who are in third years, right, you might have recently studied, you might have recently evaluated average noise power as actually what? Rx of 0, right? Right, maybe you might have studied this. So mean square value is Rx of 0. What does that mean in this autocorrelation? So in this case, the mean square value will be the value of autocorrelation function at tau equal to 0. So that will be equal to what? 50. So this is nothing but average power. So mean value square is DC power, that is Rx of tau at tau equal to infinity, and mean square value is Rx of 0. So and one more result is, it's not actually what? A property, right? Variance or sigma x square. So variance sigma x square, it will be, we already have this result, mean square value minus mean value square. Variance will be mean square value minus mean value square. So these are the properties of autocorrelation function, right? So now I've considered only about a continuous uh, random process. This random process can be discrete also, right? Random process can be discrete also. In that case, right, autocorrelation function in discrete case, right, what happens is this integration, right, it or becomes summation in this, and instead of this random process taking continuous values, it will be taking only discrete values. So in that case, normally we'll represent it as Rx of k. This will be expectation of xn and xn plus k, right? So this is x at time instance n, and this is x at time instance n plus k. This both n and k will be actually what whole numbers, right? Both n and k will be whole numbers. So just keep this result mostly from right. You may get some right. At times they used to ask find autocorrelation of they may give a time sequence and they may ask you to find autocorrelation for k equal to this, right? So, but anyhow, I don't think we have enough time to solve such problems. That you'll, I believe you will be able to. What by the time you are ready, okay to evaluate convolution and all those aspects, right? You will be able to evaluate autocorrelation function also, right? Okay, so now we'll move on to the next part, right? So next very important part is actually what power spectral density. Power spectral density, we'll write it as PSD, right? So it is nothing but what power per unit bandwidth. So its unit is watts per hertz, right? Power spectral density is power per unit bandwidth. Its unit is watts per hertz, right? So it is defined. So maybe if we have a random function x of t, its Fourier transform is capital X of f, right? Fourier transform S of f. Then power spectral density of this random process, right? It is defined. It will be denoted as Sx of f. In some textbook they are using s double x of f, whatever. So we'll be using the notation Sx of f, right? So this will be, it is by definition, it is limit, right? T tends to infinity. T is typically actually what period, right? If we are considering that random process as a periodic signal, right? And if limit T tends to infinity, mod of x of f square divided by T, right? So this is the definition of power spectral density. So this mod of x of f square will be actually what it will give you. It will be energy, right? And energy per unit time. Energy per time will be actually what say power, right? So it's actually what power spectral density. This is how it is defined. So why I told this definition is from this definition we'll get 2-3 properties of power spectral density, right? Follows from this definition only, right? So this is by definition, and please keep in mind normally, right? We won't be evaluating PSD using this definition, right? We'll be evaluating in some other means, right? So and properties, right? First one is excess of f will be always greater than or equal to 0. It will be always positive. It's of course, if you see the definition, right? If you see the definition of Sx of f, it is actually what mod of x of f square. Mod of x of f will always be positive. So Sx of f also will be always positive, right? So and any signal will have some power or some energy, right? If you are telling about a signal with zero energy or zero power, which means such a signal does not exist. So power spectral density will always be positive, right? Then second property is Sx of f is always real, always real. This again follows from definition. If even if x of f is complex, if you take mode of that, that will be actually what real. If you're taking square, right, that again will be real. So x of f is always real. That is another property, right? Then we have very important property that is called Einstein Wiener-Kingen theorem. Einstein Wiener-Kingen theorem. It says actually what power spectral density is Fourier transform of. This is the most important result, right? Possible density is Fourier transform of autocorrelation function. So if you take inverse Fourier transform of autocorrelation function, you will get inverse Fourier transform of power spectral density, you will get autocorrelation function. So which means this will be equal to integral minus infinity to infinity Rx of tau, right? E power minus j 2 pi f tau d tau, right? So by definition, right? So if you take Fourier transform of photocorrelation function, you will get power spectral density. This is again another very important result, right? So then our fourth result is, right, area under power spectral density is power, right? Area under power spectral density is power, which means P is equal to, if you integrate power spectral density from minus infinity to infinity, xx of f df, right, you will get total power. So if it is in terms of it, at times it can be what given as xx of f, or it can be given as sx of omega, right? If it is given as sx of omega, you can write it as 1 by 2 pi integral omega from minus infinity to infinity, say sx of omega d omega. So I'll be confining our discussion to what this, maybe depending upon the problem which we discuss, right? We'll be using either of this. If it is given as sx of omega, right, we'll be integrating with respect to omega and dividing it with 2 pi. If it is xx of f, right, like this. Then fifth property is actually what? Response, right? So in fact, this is the last maybe theory point which we'll be discussing. After this, we'll be solving problem, right? So response of LTI system, right? Suppose we have a linear time invariant system with impulse response h of t, right? And if you're giving a random signal x of t as its input, and you're getting output as y of t, right? And if you know Sx of f is the power spectral density of x of t, and Sy of f is power spectral density of um, this y of t, then Sy of f is related to Sx of f as, so there are two results which you have to remember. One is what will be the output power spectral density. Sy of f will be, right, mod of h of f square times Sx of f, where h of f is nothing but what? Transfer function, Fourier transform of this h of t, right? That mode of the transfer function square times input spectral density will give you output power spectral density. So maybe, right, you might have studied this in third year while you were studying about noise performance of FM, AM, and all those things, right? So this aspect you might have used, right? So then one more important result is expectation of y of t, right? Expectation of y of t, it is equal to capital H of 0. So please remember, it is capital H of 0, which means in transfer function h of f is equal to 0, right? So the capital H of 0 into e of xt, right? Capital H of 0 into e of xt. So these are the right, very important results. And maybe one more result you might have already right, familiar with that. I think I should discuss that also, right? And if you can, if you would allow, last 15 minutes we'll try to solve some 2 or 3 problems, right? So then now this is property number 5, and that 6th property would be, right, 6th property would be, right, so if the power spectral density of x of t is Sx of f, then power spectral density of x of t multiplied with cos 2 pi fct, right? This is again a very common occurring topic. Then the PSD will be 1 by 4. It follows straight away from the definition and modulation property of Fourier transform. So maybe signals and system will be handled by Mamta ma'am later. So at that time, right, you will be able to relate with that. I'm not going to discuss that in deeper, right? So now I'll just list down the result here. That will be Sx of f minus fc plus Sx of f plus fc. This is actually what follows from modulation property of this Fourier transform. If you multiply with cos 2 pi fct, the spectrum will be shifted to plus fc and minus fc. So as this PSD is mod of x of f square by t, right? So it will be right, 1 by 4, right? Sx of f minus fc, Sx of f plus fc. So instead of this, if it was sine 2 pi fct, if it was sine 2 pi fct, right? So this is same. Instead of plus, right, it would have been minus, right? So instead of plus, it would have been minus if it is sine 2 pi fct. So these are the results, right? So now, right, maybe I'll pause just for 30 seconds, and if I may ask, right, anything, right? I know I have been going a bit fast. Whether you were able to take down whatever I've written in this?
Yes, sir.
Yes, right. So if you were able to take down, okay, fine, right. So now shall we solve some problems?
Yes, sir.
Right. With the, so we'll maybe right. So one problem, right. So it is again a previous gate question, right? It was a linked question, right? So from with one data there were three questions linked, right? So maybe we'll solve that problem first, right? And some problems related to probability density function, probability distribution function, and right, all those aspects maybe later, right, when you are studying about probability, right? uh, you can do maybe that part is not exactly if you see the gate syllabus, it starts from random process, auto correlation, spectral density, and response of LTI systems, right? So we'll start with our problems, right? So problem one, right? So a given an autocorrelation function, right? Okay. Right, an autocorrelation function is given like this, right? So this is equal to, this is 50 and this is 10. Sorry, this is say 20, right? This is 20, and this is minus 10, this is plus 10, and this is tau, and it goes all the way to plus infinity and minus infinity, and this is our Rx of tau, right? Rx of tau, right? So the question is, autocorrelation function of a stationary ergodic random process is shown below in the figure, right? So this is ACF of a stationary process, right? Stationary random process. You have to find what is the mean value, right? You have to find E of x, right, or mu x, and second one which you have to find is E of x square of t, right, and third one which you have to find is sigma x square. Do you want to give it a try how to find this, or should I only go ahead and discuss? Right, this follows straight away from the property. Even I actually, what while discussing the properties, I've mentioned this, right? So maybe right, I'll first question solution, right? First question, what we have is from the properties of our autocorrelation function, mean value square, right? What was can anyone tell me what is mean value square by property of autocorrelation function? It was limit tau tends to infinity Rx of tau, right? Limit tau tends to infinity Rx of tau, right? So in this case, what is that? As tau is tending to infinity, it is equal to 20. So mean value square is equal to 20. So from this given autocorrelation function, we can find as tau tends to infinity, Rx of tau as actually what is maintained at 20. So mean value square is equal to 20. So what will be mean value? Mu will be root of mean value square. So that will be equal to root 20. So it is straight away we got it. It's equal to root 20, right? Is it clear how we got this? Right. So
Yes,
yeah,
sir.
okay. Then second question is, what is E of x square t, right? E of x square t, that is mean square value, right? How to find mean square value? By property, we have E of x square of t, right? This is equal to Rx of 0, right? E of x square t is actually what? Average power, right? Or else average power delivered to a 1 ohm resistor or whatever, right? So this Rx, this is equal to Rx of 0. So in this case, Rx of 0, right? When tau equal to 0, this is equal to 50, right? So that is equal to 50, right? Rx of 0 is equal to 50. So mainly you can see, if you refer back previous year gate questions, most of the problems, even if it is from Fourier transform, Laplace transform, or this spectral density or autocorrelation, the problems are asked based on the property, right? Not right. So you should be thorough with the properties, right? So then you will be able to solve the problems very easily, right? So that is Rx of 0, that is equal to 50 now. Then what will be variance? It's again straightforward. Variance is, we know, mean square value minus mean value square. So mean square value, we know it is 50, and mean value is equal to, actually mean value square is equal to what? 20. So this is equal to 30. So normally what we tend to do is, if we are not trying to use the property, instead of that, when we know this E x square of t is average power, so then what we'll tend to do is we'll try to take actually what? Fourier transform of this, then find Sx of w, then we'll integrate from minus infinity to infinity. That is actually what? Time consuming. That even though you may end up getting correct answer, but it's going to be very difficult, right? Of course, finding this Fourier transform itself will take a lot of time. So, right, mostly the questions will be based on properties, right? So please do keep that in mind. So this first problem, is it clear? First problem, is it clear?
Yes, sir.
Yeah, okay, fine. And then we'll right, and this is one set of problem. Maybe they may give Rx of tau or excess of tau, right? And then they may ask you to find mean, variance, right, or average power, DC power, all those things, right? And one more problem is, I told, if x is a random variable, we can have function of random g of x, right? So we'll get, so they'll tell x is a random variable, it has this autocorrelation function or power spectral density, right? And they'll give a function of this, and they may ask you to find these things, right? That is another set of problems which you may get, right? So we'll try and solve such a problem now, right? So maybe for a zero mean, right? So given, I'll just write the statement only, right? Given mu x is equal to 0, it's a zero mean, and White's and stationary process, given it is White's and stationary. So whenever it says actually what White's and stationary, right, irrespective of the time range which we are taking, the mean will be a constant. The mean will be a constant, right? Mu will be constant throughout, right? Mu will be constant. So that right, if they have given White's and stationary, that is the thing which you have to keep in mind. Also, autocorrelation function is autocorrelation function will be a function of time difference, right? So White's and stationary process, and it's x of t. X of t is a random process, and its power spectral density xx of omega, it is given to be equal to 2 by 1 plus omega square. So now here it is given as sx of omega, right? So it is 2 by 1 plus omega square for all values of omega. So this is the power spectral density, 2 by 1 plus omega square, right? And another random process, say y of t, right? So these things are given for x of t, right? A random process x of t has mean equal to 0 and power spectral density this, and another random process y of t, right? It is defined as, right, k from 0 to 2, right, x of t plus k. So instead of the summation, at times it can be actually what? Derivative of something, right? Or at times it can be integral. So in those aspects, what you should keep in mind is right, okay, maybe if it is derivative or integration, right, in frequency domain, those becomes actually what? Linear operations, right? So then you go ahead and expand it, you will be getting answer. Maybe we'll take this example. If possible, I'll solve some more questions in group. You can try and solve it, right? So e of k from 0 to 2, x of t plus k. This is y of t. The question is, we have to find variance of y of t, right? Find variance of y of t. So can I go ahead and complete this problem now? It's already 4:54, right? Can I complete this? Or else, if you
Yes,
want,
sir.
you can leave it. I'll make the recording available. Those who want to leave can leave, not a problem. I'll make the recording available. But anyhow, I'll be solving this at least for this recording sake. Right. So now, variance of y of t is what we have to find out. Right. Variance of y of t is what we have to find out. So we'll just note down what is given. E of x of t, it is equal to 0, right? And what else is given? Xx of omega, it is given to be equal to 2 by 1 plus omega square. So luckily it is actually what a standard right uh, function, right? So okay, so then what else is given? Y of t is summation k from say 0 to 2 x of t plus k. So I can just go ahead and expand. So as there are only what k equal to 0, k equal to 1, and k equal to 2, right? If you substitute k equal to 0, 1, and 2 and add it, write it as a sum, we'll get that. So it will be x of t. When k equal to 0, it will be x of t, plus when k equal to 1, it will be x of say t plus 1, right? And when k equal to 2, it will be x of t plus 2. So what is the meaning of x of t plus 1, x of t plus 2? These are actually what random variables at different dimensions, x of t plus 1, x of t plus 2. But as the question says w, it's a WSS process, right? Mean of these things will be actually what? Constant. That's something which you have to keep in mind. So y of t is x of t plus x of t plus 1 plus x of t plus 2, right? Now what we have to find? Variance of y of t. We need to find variance of y of t, right? So variance of y of t will be actually what? Mean square value of y of t minus mean value of y of t the whole square, right? So we should find mean square value of y of t and mean value of y of t. So how to find a mean value of y of t, right? So maybe mean of y of t, or I'll write, right? So this is e of y of t, and this is e of y square of t, or y of t square, right? So first we'll find what is e of y of t, e of y of t. So you don't have to what see, you just straight away, right? Y of t is nothing but what? E of x of t plus x of t plus 1 plus x of t plus 2, right? So as it is a like linear operator, it is e of x of t, sorry, right, e of x of t plus e of x of t plus 1 plus e of x of t plus 2, right? E of x of t plus 2, right? So now we know what is e of x of t. It is already given, it is equal to 0. What is e of x of t plus 1? As it is a Whitson stationary process, even if there is a time shift, right, mean will be same, so that will be 0, right? This will be 0, so this mean is equal to what? 0. So this mean value is 0, so this variance will be equal to what? Mean square value now, right? So now we have to find what is the mean square value, right? Mean square value is nothing but what? E of y of t square. So this will be equal to what? E of, right, y of t is nothing but, right, I'll write x of t plus say x of t plus 1 plus x of t plus 2, right? X of t plus x of t plus 1 plus x of t plus 2, right? This entire thing square, right? This entire thing square. So you can expand it as a plus b plus c the whole square. You can expand it as a plus b plus c the whole square. So it will become, right, e of x square of t plus x square of t plus 1 plus x square of t plus 2 plus 2ab plus 2bc plus 2crh. So it will be 2 times x of t times x of t plus 1 plus 2 times x of t plus 1 into x of t plus 2 plus 2 times x of